All right, hi everyone. My name is Zachary Roussel. Here is my Barrett 2020 summer research project, the impacts of land use on urban heat and microenvironments. And I was advised on this project by Dr. Gregory Rowengold and Jeremy Matt. So the contents of this presentation are going to be, first, I'll talk about urban heat islands. Then I'm going to talk about constructing a low-cost and multi-purpose sensor. Then I'll talk about collecting my data, my mobile sensor results, and then my stationary sensor results. So first, urban heat islands are characterized as areas that experience increased heat compared to nearby rural areas. This can be heavily attributed to the wide-scale use of impervious surfaces in urban areas. Impervious surfaces being surfaces that fluid cannot travel through, for example, asphalt, concrete, and buildings. Increased temperatures have the potential to cause devastating health effects for humans and wildlife nearby. And these effects include increased water temperature, increases in ground level ozone, and increased greenhouse gas emissions. And research like this exists in Burlington, but not on a microenvironmental scale, where a microenvironment is just a small environment that you can analyze more easily. And that's the gap that I'm seeking to fill with this research. And here is a figure of the temperature distribution over a city, where you can see that the downtown area has the hottest temperature, which is about 5 degrees hotter than the rural areas nearby. And that's not my specific data, but this is an example of an urban heat island. So why is it important here in Burlington specifically? One, our summers are getting hotter. And although Burlington doesn't have many hot months, in recent years, summers are getting increasingly warm. Research indicates an average increase of more than 2 degrees Fahrenheit in the last century. And with the impact of climate change, we can expect the worldwide temperature to further increase. Increases in temperature also prompt the use of more energy for cooling homes and businesses. So therefore, it's important to understand how the environment we build impacts the temperature. Two, Lake Champlain's health is important. With an increase in the ground temperature, water traveling on impervious surfaces will heat up the water entering the lake, potentially making it less suitable for native fish and disrupting biological processes. Also, 200,000 people depend on Lake Champlain for drinking water. Three, urbanization is the future. Urbanization is becoming an increasingly viable solution to combat climate change, and when building cities, the idea of urban heat should be considered in all contexts. Four, public health and thermal comfort are important. And as urbanization is becoming a key solution to slowing climate change, it's important that cities are healthy places for people to live, especially for economically disadvantaged populations. They experience issues with heat and urban heat more than any other population, and they need to be protected by the designers themselves. And five, urban heat exists in microenvironments. So small changes in land use, such as a flat patch of grass next to an asphalt parking lot, could present a variation in temperature. And it's important to know that this impact exists and the extent to which it impacts the surrounding area. So the research questions that I'm going to be addressing are, what is the impact of land use on the temperature? To what degree do impervious surfaces impact temperature? How far does the increase in temperature due to impervious surfaces extend? And how does the rate at which temperature decreases differ? So I'm going to go through this quickly, but basically my research demanded multiple sensors that would be taking data at the same time, and many sensors that are used in the field are very expensive. So in order to do this, I decided to create my own sensors. I built 6 Raspberry Pi 4 sensors using the Adafruit Ultimate GPS receiver and the Max 31855 thermocouple receiver that you can see here. And these 6 sensors all measure the air temperature and the GPS location, and they can be used for both stationary and mobile measurements, and they cost around $200. And then the intended use for the stationary sensors would be to put them on poles, like shown to the right, and then the mobile sensor can be put in a bag with the thermocouple coming out with the PVC pipe to block the sun. If you have any more questions, we can address those after. Testing with the mobile sensor records the temperature and the GPS coordinates every second. So experiment 1 will be walking across different types of land use while recording the temperature. So the results from my first mobile sensor test are from 12:08 to 12:54 on July 10th on the UVM campus. So this is a larger scale image of my entire route with the labeled rectangles. On the next slide, I will zoom in on each of these rectangles and talk about the specifics of the temperature changes there. First, we'll talk about image 1 all the way to the left. As you can see, when you're walking by the Waterman Green, you have a 2 to 4 degree temperature decrease in the yellow dots compared to the orange dots on either side. The orange dots are surrounded by asphalt and buildings, whereas the yellow dots are surrounded by, on one side, a road and the other side, grass. And you can see the temperature decrease as you're walking by the grassier area. In image 2, between the Marsh Life Sciences building and the Davis Center, you can see a spike in the dark orange dots there for a 2 to 4 degrees temperature increase as well. That can be attributed to the amount of impervious surfaces in the area and the surrounding buildings trapping in heat. And then you see an immediate decrease as you walk by the green ahead and with the yellow dots. Again, while crossing Main Street, we can see the darker orange dots for a 2 to 4 degree temperature increase as you're walking over the asphalt. And then the image all the way to the right, image 4, behind the Catholic Center and the Interfaith Center, you see the lowest temperatures of all these readings, and that those are all covered by trees. And although there's asphalt there, the tree coverage contributes more heavily to the temperature in that case. So this is that same route. From 122 to 153 on July 10th as well. And on this next slide, we have the 4 rectangles again in the exact same spots. We're seeing the same patterns in all of these images. For the most part, I'd just like to point out in image 3 that we also have an increase in temperature lower down University Heights that we didn't have in the previous image. This can be attributed to it just being warmer at that time at 122 versus at 1208 when I first walked by, and the radiation being collected more by the cement there. So for my statistical analysis, I'm going to go through this quickly. If we have any questions, I can address this at the end, but basically I used ArcGIS to perform buffer analysis. So I created a buffer of a specific radius around each point, and then I quantified the area of impervious surfaces within that buffer radial distance. So these are from the same data set from 1208 to 1254 on July 10th. In the top left, I have the temperature in Fahrenheit versus the area of impervious surfaces in meters squared at a 2-meter buffer. In the top right, the same at a 5-meter buffer, and at the bottom, a 15-meter buffer. All 3 of these plots have slopes that are greater than 0 and p-values that are less than 0.05. So therefore, there's a statistical significance at a confidence interval of 95%. That there is a relationship between the increase in temperature and the increase in area of impervious surfaces. From 122 to 153, we see a similar trend in the 15-meter buffer, but we have a negative slope at the 2-meter buffer, and we have a p-value of greater than 0.05 at the 5-meter buffer. The 2-meter buffer issue can be attributed to potentially shade or other things that are nearby that are changing the temperature at a small scale, and the 5-meter buffer for the same reason, but the 15-meter buffer for both was statistically significant and had a positive slope. So my conclusions are, quantitatively based on the images, temperatures appear to be highest near large roads and large areas of impervious surfaces, and at a 5% significance level, there is a positive correlation between the increase in the area of impervious surfaces and increase in temperature in 4 of the 6 plots. So the increases in temperature also depend on more factors than just the area of nearby impervious surfaces. Moving forward, I'd like to monitor temperature changes due to larger scale changes in land use, because the 15-meter showed the most accurate correlation with an increase in both the temperature and the area of impervious surfaces nearby. I like to collect data after sunset because that's when there's going to be larger changes, and analyze land uses beyond just impervious surfaces. So next I'm going to talk about testing with my stationary sensor. The goal of this sensor is to track the temperature change overnight, and it'll record the temperature every 10 minutes over extended periods of time. These are my testing locations. On the left, we have the Waterman parking lot and the Waterman Green, labeled Waterman Lot and Waterman Green. The top right, we have the Vody parking lot and the Fleming Grass. And then on the right, we have Centennial Woods, a centennial tree, which is on a tree at the outskirts of the parking lot. And then we have a sensor in the middle of the Centennial parking lot. For time reasons, I'm only going to go through a few of these data sets. But here we have from 6 p.m. to midnight, we have a large increase in the Centennial lot temperature, where the Centennial Woods temperature decreases more slowly at a linear rate, where the Centennial lot decreases very quickly. And then on the other hand, for the Vody lot and the Fleming Grass, we have the spike in the beginning in the temperature at the Vody lot, and then the Fleming Grass, we have a steady decrease in temperature. The temperatures are about equal after the first hour for both sensors. On August 2nd, we see on the left that the Centennial lot has a larger temperature than the tree on the outskirts of the parking lot. And then below that, we have a sensor that is actually in Centennial Woods, and we can see the gradual decrease as we leave from the parking lot, go towards the woods, that the temperature is decreasing. And then on August 3rd, we have a similar pattern where the Centennial parking lot, it has a greater temperature for the first 2-ish hours, and then it is decreasing at a similar rate to the Centennial Woods, and the same thing for the Fleming Grass in the Bodie parking lot. So our conclusions based on that is that the parking lots tend to remain warmer than the grass fields nearby throughout the night. The temperature over impervious surfaces tend to get cool very quickly, while the grassy areas had a more linear decrease. And around 7 to 8 p.m., the rate at which temperature decreases were very similar. And moving forward, I'd like to use more sensors to get a better understanding of how temperature changes at varying lengths from a particular land use, such as I did once at the Centennial lot parking lot with the Centennial tree sensor. And then I'd like to collect more data on hot, sunny days. So to conclude, in summary, of the 6 plots examined, 4 reported a statistical significance in the positive relationship between an increase in temperature and an increase in the area of nearby impervious surfaces. Changes in temperature are dependent on other factors, more than just the impervious surfaces nearby, which we saw with the tree cover in the mobile testing. Grassy areas had a more linear decrease in temperature, whereas parking lots decreased very quickly. And our last conclusion is that the temperature and impervious surfaces had a statistically significant relationship at a 15-meter buffer in both tests, which means that in the future, I would like to analyze larger changes in land use to see if it was due to this 15-meter buffer or if it was just bad data in that time. And then I'd like to collect data on hotter days, because a lot of the days were mostly cloudy and partly cloudy where I collected data. And then here are my acknowledgements. I'd like to thank Dr. Rowengold, Jeremy Matt, James Catalan, Brittany Antizak, Dr. Garcia, and the Barrett Foundation for everything with this project. And here are a few of my references.